Hello friends, welcome you all to the 35th lecture on function analysis and its applications. In this lecture, we will discuss the orthogonal complement of an orthogonal complement. This is the content of today's lecture. Orthogonal complement of an orthogonal complement. Okay. In 34th lecture, we have discussed the orthogonal complement. Orthogonal complement, if yes, is subset of a Hilbert space H and let X belonging to H, then S perpendicular, that is orthogonal complement of S, is defined X belonging to H such that inner product of XY is equal to 0 for all Y belonging to S. This lecture, we start orthogonal complement of an orthogonal complement. Let S be a non-empty subset of a Hilbert space H, then S perpendicular is a subspace of H. We define perpendicular of S perpendicular, written by S double perpendicular. It is defined by S double perpendicular equal to X belonging to H such that inner product of XY equal to 0 for all Y belonging to S perpendicular. Here S perpendicular defined this. Here inner product of XY is equal to 0. Here X is the element of H and Y is the element of S. Here perpendicular of S perpendicular, that is meaning of this is S perpendicular and perpendicular. Okay, so as per this definition, X belonging to H and Y is the element of S perpendicular. Okay, this one as per this definition. So S double perpendicular defined as like this. So perpendicular of S perpendicular, that is orthogonal complement of an orthogonal complement. Theorem: if S, S1, S2 are non-empty subset of a Hilbert space H, then prove the following. Perpendicular of the singleton set 0 is equal to H. Second, perpendicular of H is singleton set 0. Third, S intersection S perpendicular is singleton set 0. Fourth, S1 proper subset of S2. This implies that S2 perpendicular is proper subset of S1 perpendicular. And fifth, S proper subset of S double perpendicular. Let us prove it. First we prove perpendicular of singleton set 0 is equal to H. In this case, here perpendicular of singleton set 0. Okay, it means here S perpendicular is perpendicular of singleton set 0. So S perpendicular defined by this. So 0 perpendicular can be defined X is the element of H such that inner product of XY is equal to 0 for all Y belonging to singleton set 0. That is Y is equal to 0. Thus X belonging to H. This implies that X belonging to perpendicular of singleton set 0. Therefore, H is proper subset of perpendicular of singleton set 0. Since orthogonal complement is only the subset of H, then perpendicular of singleton set 0 is subset of H. Here H is subset of perpendicular of singleton set 0 and here Perpendicular of singleton set 0 is subset of H. Hence, perpendicular of singleton set 0 equal to H. Second we have to prove H perpendicular equal to singleton set 0. So let X belonging to H perpendicular. Then by definition of H perpendicular equal to X belonging to H. Inner product of xy is equal to 0 for all y belonging to H. Okay, here X belonging to H, also y belonging to H. So we can write this definition in reverse way. Y belonging to H, and also we know that if inner product of xy is equal to 0, then inner product of yx is equal to 0. So we can write this, and x belonging to H here. So this definition can be written as this. Therefore, x is equal to y. Okay, if x is equal to y, so inner product of xx equal to 0. Inner product of xx defined norm of x square is equal to 0. This implies that x is equal to 0. Thus, x belonging to H perpendicular. This implies that x is equal to 0. Therefore, H perpendicular is singleton set 0. Third, S intersection S perpendicular is singleton set 0. Okay, we have to prove it. Any x belonging to S intersection S perpendicular. This implies that x is the element of S and x is the element of S perpendicular also. Okay. Since x belonging to S perpendicular, therefore x is orthogonal to every vector in S. Since x belonging to S also, then x is orthogonal to x itself. That is, S perpendicular equal to x is the element of H such that inner product of xx is equal to 0 for all x belonging to S. Okay. So inner product of xx is equal to 0 if and only if x is equal to 0. Thus, 0 is the only vector which can belong to both S and S perpendicular. Hence, S intersection S perpendicular is proper subset of singleton set 0. If S is subspace of H, then 0 vector is the element of S. Also, S perpendicular is subspace of H. Therefore, 0 is the element of S perpendicular. Thus, if S is subspace of H, then 0 is the element of S intersection S perpendicular. Therefore, in this case, S intersection S perpendicular is singleton set 0. Fourth, let S1 is proper subset of S2. Let S belonging to S2 perpendicular. This implies that X is orthogonal to every vector in S2. This implies that X is orthogonal to every vector in S1 also, because S1 is subset of S2. This implies that X is the element of S1 perpendicular. Okay, so X belonging to S2 perpendicular, this implies that X belonging to S1 perpendicular. Therefore, S2 perpendicular is proper subset of S1 perpendicular. Fifth, we have to prove S is subset of S double perpendicular. Let X is the element of S, then we can write S perpendicular equal to y is the element of H such that inner product of y x is equal to 0 for all x belonging to S. Okay, that is y is the element of S perpendicular. Okay, hence if y belonging to S perpendicular, then from the definition of S double perpendicular is defined as S double perpendicular equal to x is the element of H such that inner product of xy is equal to 0 for all y belonging to S perpendicular with this. Okay. So here x is the element of S double perpendicular and y is the element of S perpendicular. Here missing, here x double perpendicular. Okay. Thus, x is the element of S. This implies that x is the element of S double perpendicular. Therefore, S is the subset of S double perpendicular. Noting point. If M and N are subspaces of a Hilbert space H and M perpendicular N, then M intersection N equal to singleton set 0. For if suppose that M intersection N not equal to singleton set 0, let X belonging to M intersection N. Since X is the element of M and X is the element of N, therefore M perpendicular N, this defined inner product of x is equal to 0. So this implies that norm x square is equal to 0. That is x is equal to 0. Okay, so x is equal to 0. Therefore, M intersection N is singleton set 0. Next theorem. If M is a proper closed linear subspace of a Hilbert space H, then there exists a non-zero vector Z0 in H such that Z0 perpendicular to M. Proof. Since M is a proper subspace of H, therefore there exists a vector x in H which is not in M. Let d be the distance from x to M. Then by definition of distance, we have d is equal to d of x and subset M equal to infimum of the norm x minus y such that y belonging to M. Already we have discussed the distance between the points of Hilbert space H and subspace M in earlier lecture. Now y cannot be equal to x because x not element of M. Therefore d greater than 0. Since M is a proper subspace of H, therefore by theorem second of lecture 32, there exists a vector y0 in M such that norm x minus y0 is equal to d. Now we set z0 is equal to x minus y0. We have norm z0 is equal to norm of x minus y0 equal to d, which is greater than 0. Therefore, z0 is a non-zero vector. Now we shall show that z0 is perpendicular to M. Let y be arbitrary vector in M. We shall show that z0 is perpendicular to y. For any scalar alpha, we have z0 minus alpha y equal to z0 is x minus y0. So this can be written as x minus y0 minus alpha y. That is x minus y0 plus alpha y. Since M is a subspace of H and y0, y belonging to M, therefore y0 plus alpha y belonging to M. Then by definition of D, we have norm x minus y0 plus alpha y greater or equal to D. Okay. Here definition infimum of norm x minus y. Okay. So that is norm of x minus y greater or equal to D. So as per this, we can write norm of x minus y0 plus alpha y greater or equal to D. Now, norm of z0 minus alpha y, that is norm of x minus y0 plus alpha y greater or equal to D. D is norm of z0. Okay. This implies that this is greater or equal to norm of z0. That is squaring both sides. We have square of the norm z0 minus alpha y greater or equal to square of the norm z0. Okay. So we know that norm x square is equal to inner product of xx. Okay. So this can be written as inner product of z0 minus alpha y, z0 minus alpha y. This is also inner product of z0, z0, and this portion left hand side, so this is greater or equal to 0. Okay. So simplifying this, using the force property of inner product, we have inner product of z0, z0 minus inner product of z0 alpha y minus inner product of alpha y z0 plus inner product of alpha y minus inner product of z0, z0, which is greater or equal to 0. So again, using the third property of inner product, this implies that inner product of z0, z0 minus alpha bar outside the inner product minus alpha bar into inner product of the z0 y minus alpha into inner product of y z0, and this is alpha and alpha bar into inner product of y minus inner product of z0, z0 greater or equal to 0. So this inner product of z0, z0 negative and this is positive, that is cancelled out. Now we have this one greater or equal to 0. So equation 1 is true for all scalars alpha. Let us take alpha is equal to beta into inner product of z0 y, where beta is an arbitrary real number. Then alpha bar equal to beta, that is real. So beta bar is equal to beta. So alpha bar is equal to beta into conjugate complex of inner product of z0 y. Putting the value of alpha and alpha bar in equation 1. Here alpha and this is alpha bar. Putting in equation 1, we get minus beta into inner product of z0 y bar into inner product of z0 y minus beta inner product of z0 y into inner product of z0 y bar plus beta square inner product of z0 y into inner product of z0 y bar norm y square greater or equal to 0. Okay. Because inner product of y is equal to norm y square. or this can be written as this and this same. And also we know that z bar is equal to mod z square. Okay, so these two terms can be written as minus 2 beta into modulus of the inner product of z0y square plus beta square of the modulus of inner product of z0y into norm y square greater or equal to 0, or here common of beta into square of the mod of inner product of z0y. Here we have beta into norm y square minus 2. This is greater or equal to 0. Equation 2. The relation 2 is true for all real beta. Suppose that inner product of z0y not equal to 0, choosing beta to be positive and so small that beta into norm y square less than 2. We see that from 2 this one. Okay, reverse inequality. Beta into square of the mod of inner product of z0y into beta norm y square minus 2 less than 0. This contradicts equation 2. Hence, we must have inner product of z0y equal to 0. Okay, which means that z0 is perpendicular to y. Thus, z0 is perpendicular to y for all y belonging to M. Therefore, z0 is perpendicular to M. In this lecture, we have discussed the orthogonal complement of an orthogonal complement and related theorems. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Naresi. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Waterroutine. Thank you.